Hello everyone, welcome back to our channel, and today we are going to tackle a new LeetCode problem called shortest unsorted continuous subarray. This will help you with array manipulation as well as sorting techniques along with using two pointer technique to reduce time complexity. So let's dive into the problem. So let's see what the problem says. So it says that given an integer array nums, you need to find one continuous subarray such that if you only sort that part of subarray in increasing order, then the whole array will be sorted in increasing order. So you have to return the shortest such subarray and output its length. So what it says is you will be provided with an array, and in that array you have to find such part of the subarray, such continuous part of the subarray to which if you sort it, then the whole array would be sorted. So that is the problem statement. So for example, in the first example, right? So here if you see, you need to sort 6, 4, 8, 10, 9 so that your entire array becomes sorted. Because here if you see 2, 6, it's okay, it's sorted, right? It is increasing, but suddenly it became unsorted from 4. So that's why this is unsorted, right? 6, 4, 8, 10, 9, these are unsorted. So you have to sort it to make it sorted. Okay. In example 2, it is already sorted. The shortest subarray for which we have to get the arrays sorted is 0, because there doesn't exist any subarray which is unsorted within it. Everything is sorted. The same goes with example 3. Okay. So here I have taken one example, same here. So 2 is sorted, and then 5 is sorted, 6 is sorted. Suddenly it becomes unsorted, right? So if we sort it, then 4 needs to come here, right? Then only it will be sorted. So the shortest length of the subarray to make it sorted would start from here, because 4 is still unsorted, right? And 4 is less than 5, so it should start from here and it should go till here, right? Because 10 is again 10 correct position is here. Okay, other than this, 2 is already sorted, it is the smallest, and 15 is already sorted. So in this example, 1, 2, 3, 4, 5, 6, this 6 element needs to be sorted to make the entire array sorted. Okay. So that's our problem statement. So let's look at the approach to solve this problem. So we will look at two approaches. So first approach, we will, in both the approach we will use two pointers. So our first approach would be with sorting the entire array, and in second approach would be without sorting the entire array. Okay, so let's look at our first approach. So here in first approach, what we will do, we will be provided with an array. Suppose for example, this is my S1, right, the original list, and then I will have another list called S2. This will hold a sorted array of S1 original list, right? So we'll sort the original list and store it in another list called S2. Okay, so now what I have to do is I will keep two pointers. One is low here and one is high, which will point to the last. So I have a low pointer pointing to the initial of the array, and I have a high pointer pointing to the last end of the array. Okay, and also we'll keep the same pointer in our sorted list. So now what we will do is we'll keep on checking the original unsorted list and the sorted list. So we'll see that whether it is equal or not. Yeah, it is equal, right? So if it is equal, then we'll move forward. So this 2 is equal to this 2 from the sorted list, so we'll move forward, and similarly this will also move forward. Okay, now we will see that this is not equal, right? So the point when we see that this is not equal, we are done. We will just break it. We will not move forward. That means that we know from here it is unsorted, correct? So again we'll do the apply the similar logic from the end as well. So we'll check whether 15 is equal to 15 or not. It is equal, right? So we'll move forward towards the left. So here also we'll move forward towards the left. And now we saw that 9 is not equal to 10, right? So that's what we will not move forward. We are done. So now we know that from here onwards it will not be sorted. That's how we know that this part of the array is unsorted. Hence what we will do, high minus low plus 1. So 1, 2, 3, 4, 5, 6. So 6 is the shortest unsorted continuous subarray. Okay. So that is our approach. So let's code this solution. So initially we need a low pointer and a high pointer. So first get the nums. Then we need a low pointer and a high pointer. So low pointer will be pointing to the head and high pointer will be pointing to the tail. Now we'll first find our low pointers. We'll first find our boundary, right? So we'll say that while low is less than n, and we'll iterate till the end, right? And okay, we have to find another sorted array, right? So first is our nums, and we'll have something called nums2, which will hold a sorted part of nums. So these are nums and these are nums2. Okay. Nums2 is sorted. So what we'll do is we'll iterate for low and we'll run till it matches with the sorted array. So nums of low equal to nums of low, nums2 of low, right here. So if it matches, we'll move forward until it matches. So at till the point it doesn't match, we'll move forward. But here at any point of time, suppose consider that like for in our example 2, right? So there is no such subarray which needs to be sorted. So running this loop, it will reach the end, right? 1, 2, 3, 4. So at that point of time, we don't have to do anything. We can simply say that it have reached the end. So there is no such subarray which needs to be sorted. In that case, I can just return 0, right? So we'll apply that logic here. So we say that if low have reached the end, then we will simply return 0. Okay, this is an edge case. Okay, otherwise now we have done for low and we'll do for high as well now. So while high is greater than or equal to 0 and should be greater than 0 and nums of greater than or equal to, yeah, and nums of high is equal to the sorted value. If it is equal, so 15 is equal to 15, it will move backwards, right? So it will move backwards till the point it doesn't match. High equal to this one. And finally we got our boundary position. So this is our boundary, low and high, saying that everything left of the low is sorted and everything on right of the high is sorted. So problem arises from the low pointer and high pointer. So the entire thing needs to be sorted. So this part needs to be sorted to get the actual value. So that's why return high minus low plus 1. So we're done with the code. Let's run this. Let's submit it. Cool. Okay. But here they've asked for a follow-up, right? So can you solve it in O of n time complexity? So here if you see, since we are sorting here, right? So while sorting, it will take n log n. Correct? So this will take n log n, and the rest of the part is even less than n, but we can say n. So the higher one is our n log n. So the time complexity of this is n log n. So that's why they are asking, can you do it in O of n time complexity? Can you reduce this time complexity? Okay. So to do that, like to be able to do in O of n, let's look at another approach, or the second approach. So in our second approach, what we'll do is we'll again use two pointer techniques, but now we will not use an additional list which will be sorted. Okay, so like in previous case, we had an extra space as well, and at the same time we use n log n while sorting this, right? So we'll come up with a better approach. So in this approach, what we will do is we'll first try to find our boundary. Okay, so by boundary, what I mean is such position after which it start becoming unsorted. Okay, so let's look at this example. So first, if you see from the beginning, if I'll take the low pointer, then we'll keep on moving until it is sorted, right? By sorted, it means if it is increasing. So 2 is increasing, right? 2 is less than 5, so we'll increment it. 5 is less than 6, right? So it is increasing, we'll increment it. But here we saw that 6 is greater than 4, right? So this is decreasing from here. So we know the boundary now. So boundary is from 6, right? So from here it has started to become unsorted. Okay, so this is till here it is fine, but from here it is unsorted. So this is our boundary. Okay, so similarly we'll move backward till the point it start increasing. Okay, so what I mean by that is 9 is smaller than 15, right? So it is sorted, so we'll move backward. Now again, 10 is 10 smaller than 9? No, right? 10 is bigger. So from this point it has started becoming unsorted. Okay, so that's why you can say that this is our boundary. Okay, so anything lies from towards the left will be unsorted. So this part of our array is definitely unsorted. Okay, that much we can see. So nothing can be shorter than this. Okay, so that's what we can guarantee from here. Okay, so we'll do that. And now after finding this, is it okay to say that this is our length, only this part needs to be sorted because it was increasing till here and decreasing from the end? No, right? Because there might be some value inside the unsorted which will lie somewhere in the sorted part as well, in between some sorted part as well, right? For example, here if you see this 4, right, this actual position needs to be after 2, correct? And this 10, its actual position needs to be after 9. Okay, so that's why now what we will do is that inside this unsorted part we'll try to find the minimum value. Okay, so here we clearly know that 6, 4, 8, 10, 9, out of these values 4 is the minimum, so our minimum is 4, right? And what is our maximum? Our maximum is, out of 6, 4, 8, 10, 9, 10 is our maximum, right? So now what we'll do is from the sorted part we'll try to put this 4 in the correct position, or rather I would say instead of putting it, we'll try to find the exact position of 4. So by that we'll know that from that is the problematic part from where it has we need to sort it, right? So what is the correct position of 4? This correct position of 4 is here, right? And the correct position of maximum 10 towards the right is here, right? So that's what, for when we found that what is the current position of min in the left side and current position of max in the right side, then we were done, because the correct position of min in the left side is our actual boundary, which is this, and our correct position of max in the right side is our actual boundary, which is this. So finally we can say that this is our boundary. Okay, and what is the length of this boundary? It is this high, we will move high till here, right, while trying to find the actual position of max in the right side, and actual trying to find the actual position of min in the left side, will move left low here, right? So in this way we can say that the length between low and high would be the max. So that is 1, 2, 3, 4, 5, 6, 6. So this is our actual logic to solve this problem. So let's do the coding now. We'll remove this. And initially we'll just move forward till the point it is decreasing. That means we'll run till the end, while low is less than n, while low is less than n, and nums of low is less than nums of low plus 1, and we'll run it till n minus 1 in that case. So here what we are saying that less than or equal to. So here we are saying that 2 is less than 5, so we'll move forward, and 5 is less than 6, so we'll move forward, but 6 is not less than 4, so we'll stop here. Okay, so that's what we did. Low plus equal to 1. Okay, and for the edge case of 1 2 3 4, so if it keeps on moving and it, it is less than it n minus 1, it reaches 3 and it finds that it is still less than 4 and it reaches the end, right? So in that case we don't have to look anything forward, we can simply return it. So if low is equal to n minus 1, because if it is monotonously increasing, that means it is already sorted, right? So if it has reached the tail, then we'll simply return 0. Okay. Otherwise, now we'll do the do it from the end. So we'll try to find the boundary till it is decreasing. So to do that, simply say while I is greater than 0 and nums of high is greater than or equal to nums of high minus 1, right? So we'll do it. So in this way we have found the two boundary, okay, but not the actual boundary. So now after finding this low and high boundary, what we'll do is in this unsorted part we will just check the local maximum and local minimum. Okay. So to do that we'll say subarray min, and for now I'll just take any number within the subarray. So I'll say simply low, and I also need a subarray max. So, and we'll check in the subarray for I in range. So we'll check from here, right? We'll check from here to here. So 6 to 9, low to high, low to high, high plus 1. And that way we'll see subarray min needs to be the minimum of the whichever is the smallest, it will hold that value. I will update that. So subarray min will be updated with the minimum value, and at the same time subarray max will hold the or update the maximum value. Sorry, it needs to be I because we're iterating, right? Nums of I or subarray max. So after this we have got our minimum and maximum within the window. Now what we'll have to do is we'll have to find what is the correct position of the subarray minimum. Okay, so in this case so we'll have to find what is the correct position of subarray minimum within the sorted part towards the left, right? Within this, what is the correct position of subarray minimum? Okay, so what we'll do is while this, right, nums of low, okay, so initially it is pointing to 6, it is pointing to 6, and we will go towards the left until the numbers are greater than 4. Okay, so here 6 is greater, right? So it will move forward. Then 5 is also greater, right? So it will move forward. So and it is that 4 is here. I mean, finally we know that after 2 the 4 should come. So here we will stop, right? So indicating that 4 needs to be in this place. So how we will do that? So we'll say that if instead of saying nums of low, we'll say that nums of low minus 1. Okay. nums of low, while nums of low minus 1 is greater than or equal to my sub array min. So what will happen? We'll just decrement it. So in this case, what will happen is first it will check with the, so our initially our after this iteration our low was pointing to 6, right? So it will check what is low minus 1. Low minus 1 is 5. Is this 5 greater than 4? Yes, it is greater. So it will decrement the low, and it will point, the low will now point to here, right, to 5, and it is 2. And now again what it will do is again we'll check whether low minus 1 is greater than 4. So now our low was pointing here, so low minus 1 is 2. So 2 is not less than 4. It is 2 is not greater than 4. It is less. So here it will stop, right? So 2 is not greater than 4. Okay, so here it will stop. So indicating that this point is our boundary. So this was supposed to be the 4 placement. Okay. So here if I say this was supposed to be the 4th placement. So that's how we are done with the left side. So similarly in the right side, what we will do is 9 and 15, right? Initially our high was pointing here, and while nums of high plus 1 is less than or equal to subarray max. Will increment our value. So here it will see that sub high plus 1 is 15. So whether 15 is greater than subarray max is first 10, right? So whether 15 is smaller than 10 or not. It is not, right? So here only it will stop. So 10 position was supposed to be here itself. In place of 9, it should be here. So that's how we are done, and finally we will return this length. That is high minus low plus 1. Okay. Somewhere we have missed the syntax. Here. Okay. Let's run this code. Cool. List index out of n. Low. Subarray min. So suppose, for example, if all the numbers are equal, then it will move ahead and it will go out of boundary. It will go out of the boundary. So for that, we'll not have an equal condition, and at the same time we'll also say that low should be greater than 0. Okay, and here high should be less than n minus 1. Okay, to be able to do it correctly. Yeah. Awesome. Amazing. So that's how we have solved this problem. And here, if we look at the time complexity, so none of the paths have more than O of n. So overall time complexity would be O of n only. So that's how we have solved this problem without using any extra sorted list, and as well as we have avoided the sorted, so it didn't go to n log n, but it I mean, using this technique we just did it in O of n. Okay. So that's how we have successfully solved our shortest unsorted continuous subarray problem. It will test your ability in the interview for with array manipulation and using two-pointer techniques, as well as I mean looking at different trade-offs like and choosing the correct approach according to the interview. So this is a very good problem for the interview. So if you like this video, if you found it is very helpful, then please give us a thumbs up and subscribe to our channel for coding questions and interview preparation. Also, don't forget to hit the bell icon to get more updates in the future. And also, if you have any suggestion or any doubt, please put it in the comment box. Thank you so much. We'll see you in the next video. Thanks a lot.